Good morning, everyone. We are going to do Module 5, Context Sensitive Grammar. Okay, Module 5 is Context Sensitive Languages and Turing Machines. Today's topic is Context Sensitive Grammar and Linear Bounded Automata. Okay, let's start the lesson. So far, we have seen up to context-free grammars, and we saw earlier itself that context-free grammars cannot, uh, implement certain languages. So now we are moving on to context-sensitive grammar, which is more powerful than context-free grammar. Okay, some languages which cannot be generated using regular grammar or context-free grammars can be implemented using context-sensitive grammars, and these grammars are used to describe more complex languages than what we saw in regular grammar or in context-free grammars. And one example is a raised to n, b raised to n, c raised to n, such that n is greater than or equal to 1. We saw that a raised to n, b raised to n can be implemented in context-free grammars, but a raised to n, b raised to n, c raised to n cannot be implemented in context-free grammars. So let's first look at the definition. Okay, it is a quadruple. G is equal to V comma sigma comma P comma S. Okay, and it is context sensitive. This grammar is context sensitive only if every production is of the form alpha tends to beta. Look at my pointer, alpha tends to beta. Okay, where alpha and beta can be a collection of the non-terminals as well as the terminals. V is the collection of non-terminals and sigma are the collection of terminals. So it's any combination of the terminals and non-terminals can be on the left-hand side as well as on the right-hand side. This form is what should be there for context-sensitive grammars, and the number of elements in beta must always be greater than or equal to the number of elements in alpha. Okay, so far we had seen that on the left-hand side, the alpha part, there was only one non-terminal. But now, combination of terminals and non-terminals are possible both on the left-hand side as well as on the right-hand side. So alpha and beta, but with one restriction that the right-hand side must have at least the number of elements on the left-hand side or more. Okay, so that is called the non-shrinking condition. Okay, the non-shrinking condition. Okay, now there is an exception, just like in context-free grammar, S tends to epsilon is not allowed unless epsilon is, and that means the empty string is an element of the language. Okay, and if S tends to epsilon is allowed, then S cannot appear on the right-hand side of the production. Okay, if S tends to epsilon is not there, S can appear on the right-hand side, but if it is there, S cannot appear on the right-hand side of the production. Okay, now the formal definition. G is equal to V comma sigma comma P comma S, where V are the non-terminals, sigma are the terminals, P are the production rules, and S is the start symbol. Okay, the production rules should be of the form U capital AV gives you small u capital B W. Okay, so U, V, and W are all elements of either capital V or sigma or a union of the two. Okay, A is an element of V, so A and B, A is one non-terminal at least should be present on the left-hand side. But on the right-hand side, it can be a collection of terminals or non-terminals or both. Okay, so that's what's being written over here. A is an element of V, which are non-terminals, whereas B is an element of V union sigma plus. There should be at least one element, but it could be non-terminal or terminal. Okay, now meaning is that A can be replaced by B only in the context of U and V. So this A is being replaced by B and W only if A is in the middle of U and V. This the order of the terminals and the non-terminals is important in context-sensitive grammar. Okay, for example, if we have a rule, small a, capital A, B gives you small a, small b, then here it means that capital A can be replaced by small b only if the left hand side of capital A is small a and the right hand side of capital B is, small capital A is small b. So if capital A appears between a small a and a small b, then the capital A can be replaced by a b. Otherwise, you cannot. That is why it is called context sensitive. All capital A's are not replaceable by b. Only if it is following a small a and preceding a small b, then it is replaced by a small b. That is why this is called context sensitive. Okay, there is a control for the substitution. Now we're going to look at some examples of context sensitive grammar. The first example and the most common example that you see in any textbook is a raised to n, b raised to n, c raised to n, such that n is greater than or equal to 1. Okay, so this is the context sensitive grammar. How we get this grammar, we are not going into details, we're just looking at an example. S tends to A, S, capital B, capital C, or ABC. That is, if n is equal to 1, then we will go directly to ABC. Okay, now if n is not equal to 1, then you should be able to expand it. So this S can either be another ASBC or this S can be ABC. Okay, then CB, small c, capital B gives you capital B, small c. So you can interchange capital B and small c. A, capital B can be replaced with AB. Small b, capital B can be replaced with BB. Small b, capital C can be replaced with BC. Small c, capital C can be replaced with CC. Okay, this is the grammar, context sensitive grammar for A raised to n, B raised to n, C raised to n. Now let's look at the string n is equal to 2. That is AA, BB, CC. We start with S. S with this first, please look at my cursor, with the first production, we are moving to S gives you A and capital S, B, C, capital B and C. And then again, this S is being expanded. Again, that S is replaced by ABC, but not ASBC, ABC, because we want only two A's. So when we replace this S with, this S with ABC, two A's will be there. Okay, so we replaced with ABC, and then this B and C is still there. Okay, now what to do with this B and C? Okay, so with CB, okay, CB, because we already have two C's, we cannot include another C. So now we are going to look at what we can do with CB. CB can be interchanged. We see this second production. So this, it has been interchanged and it becomes AAB, capital B, small c, capital C. Then we have a small b, capital B, and a small c, capital C, and we have this small b, capital B can become small b, and small c, capital C can become small c, small c. So we use those two productions and we get AA, BB, CC. Okay, we can continue like this for any n value which is greater than 1. Okay, so this is one example. Now, this is another example, A raised to n, B raised to n, C raised to n, D raised to n. Just like over here, we needed, rules for swapping and things like that. We need extra rules over here since we have 4 alphabets, A, B, C, and D. So this is our rules. And based on these rules, for n is equal to 2, we can do the expansion. Okay, how we are writing these rules, we are not going into detail. It is more complex than context free grammar. So when we look at the question papers, I will be telling you how exactly we can do. Normally, what we do is we look at what we want, the rules for, see over here, when we see we have got for each alphabet a capital letter. Okay, and then S can be expanded to give you for 1, the value 1. So over here also we do something similar. We do the first one, small a, capital B, capital C, capital D is for possible for the rule 1. And then A, capital S, B, C, D is possible for any value which is greater than 1. Okay, and then interchanging values. We need, if we have a capital C, capital B, we need to be able to interchange and make it BC. If we have a capital D, capital C, we should be able to interchange C and D. And if we have a capital D, capital B, we should be able to interchange B and D. Okay, and then once that is done, we can see that each capital B, capital C, capital D can just be replaced by, if it's a small a, capital B, it's replaced by small a, small b. If it is small b, capital B, it's replaced. So essentially these steps from 6 to 10, what we are doing is replacing the capital B, capital C, capital D with small b, small c, and small d. Okay, this is the general rule for A raised to n, B raised to n, C raised to n, D raised to n, etc. Those kind of languages. Okay, so you can try for an example. N is equal to 2. Always, once you have written the grammar, do a small example, so that if we have forgotten any particular step, we will be able to correct it over here. That is why we do derivations. Okay, so when we do the derivation, we can use the rules and see we get AA, BB, CC, DD. Okay, next we have another one. Here N, all are not of the same size. Alternate, B and D are of a different size and A and C are of the same size. So the only restriction is N and M should be greater than or equal to 1. And for that, we have modified the previous rules to get these particular values. So we have S gives you small a, capital S, C. Okay, and this S could also be U. So what we're actually doing is we are ensuring A and C are of the same number and B and D are the same number. So U can be expanded as B, U, D or B, D. Okay, so A, S, C ensures A and C are the same number and B, U, D ensures that B and D are of the same number. And then just like earlier, if there is a DC, we should be able to interchange C and D. Okay, and then each value, capital B, capital C and capital D should be replaced by BB in whichever combination they are. Okay, but A should follow a B, B should follow a C, and C should follow D. So other combination should not be there on the left hand side. So using this grammar, check for N is equal to 2 and M is equal to 3. Okay, and when you do the expansion, you can see that this grammar is successfully deriving A, B, 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 C, C, D, D, D. Okay. Now, those are some of the types. There are others also. Usually for questions in the exam, it is difficult to give you these simple ones, A raised to n, B raised to n, C raised to n. You can derive in examination and show. But for larger context-sensitive grammars, this 3 hours will not be enough. So usually we don't see such questions in the examination. Okay, so we are going to continue. Properties of context-sensitive grammar. Every context-sensitive grammar generates a context-sensitive language. So the strings that are generated using context-sensitive grammar are that of a context-sensitive language. And context-sensitive languages are recognized using linear bound automata. So for every CSG, there will be an equivalent LBA. Okay, context sensitive languages are more powerful than context free languages, but they are less powerful than unrestricted grammars. That is the next level. We will look at unrestricted grammars later on. Okay, and some of the applications of context sensitive grammar are natural language processing. It deals with agreement, subject verb agreement, things like that, so we have a context, and in the context whether the sentence is right is what we have to look. So there natural language processing, CSG are used. In complex programming language constructs, there also CSG will be used. And modeling simultaneous dependencies. So if we have multiple dependencies and we want to model those, there also context sensitive grammars will be helpful. Okay, now we are going to look at the machine. Linear bound automata is the machine which generates the, which implements context sensitive grammar, just like context free grammar was implemented using the push down automata. Okay, so linear bound automata is the automata which implements the context sensitive grammar. What is a linear bound automata? A linear bounded automaton is a non-deterministic Turing machine. So it is a linear bound automata is a subset of the Turing machine. We're going to look at Turing machines in the next topic, whose tape is restricted. So that means Turing machine's tape is unrestricted. You have as much length of tape as required. But in the case of linear bound automata, there is a restriction to a length that is linearly proportional to the length of the input. So depending on what is the size of your input, there is a restriction on the size of the tape for linear bound automata. So only those problems which can work in this restricted size of the input tape will be possible to be implemented using linear bounded automata. In other words, it cannot use, that is the linear bound automata cannot use more tape than a constant multiple of the input size. Okay, so formally what we are saying is that let the input string have this BW and have a length N, and LBA has a tape bounded by KN cells where K is a constant. So you can have constant multiples of that input length N. And the tape head cannot move beyond this bounded region. Whatever is your KN size, that is the maximum that you can use for the input. You can't do more than that. Okay, formal definition of the linear bound automata, just we learned just now that LBA is a subset of the Turing machine. So Turing machine is a 7 tuple, which we will look at later on. Here also we have a 7 tuple where Q is a finite set of states. Sigma is the input alphabet. Tau is the tape alphabet. So whatever is your input, so tau will be a subset of this sigma. Okay, delta is the transition functions. Q naught is the initial state. Q accept is the accepting states, and Q reject are the rejecting states. Okay, so this is how we have 7 tuple elements in the formal definition. Now, what are the important restrictions? We already looked at it. The first important restriction in an LBA is that the tape head cannot move beyond the input portion of the tape. So whatever is the KN size, it is bounded. Okay, so this makes it space limited, but still it is not as powerful as an unrestricted Turing machine, but it is more powerful than a push down automata. Okay, now why linear bounded? First of all, it is called linear bounded because there is a restriction on the size. So there is a maximum tape size which is linearly proportional to the input. This is crucial in the case of linear bounded automata because only those problems which can be solved by this restriction of the size can be implemented using a linear bound automata. Unlike a standard Turing machine which has infinite tape. Okay, now there is a theorem. A language is context sensitive if and only if it is accepted by a linear bound automaton. Okay, so only if a context sensitive grammar has got an equivalent linear bound automaton to implement it, then that language is context sensitive. Otherwise, it cannot be context sensitive. So both will be possible. From context sensitive grammar, we can get its equivalent linear bound automaton, and from the linear bound automaton, we should be able to design the context sensitive grammar. Okay, now the implications: linear bound automata is a subset of the Turing machine because of the restriction in the space, and a push down automata is a subset of the linear bound automata because it is more powerful than the context free machine. Okay, now let's look at this example. This is the standard example: a raised to n, b raised to n, c raised to n, such that n is greater than or equal to 1. How do we use the, remember the input? Okay, input size will be restricted. So the input that we have is A, B, 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 C, C, C. So how much is our size? Our size is 3 into 3, 9. Okay, the algorithm for the LBA should restrict whatever movements it does and transitions that it does within this 9 input space. Let's see if that is possible. First, mark the first A, that is, change it to some value. Okay, so here we are changing it to X. Then move right to find the first B that is not marked and mark that as Y. Okay, then move right again to find the first C that is not marked and mark it as Z. So after this 1, 2, 3 steps, we have marked the first A, the first B, and the first C as X, Y, and Z. Then the fourth step is to return to the leftmost unmarked A. Okay, so in this case, the next unmarked A is the second A. Okay, and repeat until all letters are marked. So again, we will do 1, 2, 3. So we will mark A as X, move to find the next unmarked B and mark that as Y, then move to find the next unmarked C and mark that as Z. Then again, we will return to the first unmarked A, that will be the third A, and that we will mark it as X. Then we will move to find the next unmarked B, which is Y, and then the next unmarked C, which is going to be marked as Z. Then if you return, there is no more place to return, there are no A's pending. So we accept if all the letters are marked. So in this input, if all the letters are either an X or a Y or a Z, then they are accepted. Otherwise, if there is anything which is not any of these input alphabets not marked, then it is rejected. So it is not A raised to n, B raised to n, C raised to n. So this is exactly matching the input size 9, the algorithm. So we have an equivalent linear bounded automaton. Okay, observation: the tape used is exactly linear in the input length. The machine never writes outside the original string, satisfying the LBA constraint of space. One more example: palindromes with equal halves. Okay, so we have W raised to R. Okay, so this will be a palindrome and the alphabets are 0 and 1. So let's say that we have the input 0, 1, 1, 0. Let's see the algorithm. Compare the first and the last symbols. If they match, mark them, say X. So we look at the first one, that is first element which is not marked, and we go to the last and we look at the last element which is not marked. If they both match, then they are marked them as X. Then move inward and repeat until then the next symbol which is last and not marked will be 1. Again, match them. They will also be X. When there is no more, to symbol, all the symbols are X, then we accept if it is fully matched and reject if it is mismatched. So here in this case, if all the values are X, all matched values are marked as X. If any value is not matched, we don't match it as X and we continue. Okay, so The restriction is there. Again, the LBA is the same size as that of the input. And so it is possible to create an LBA for WWR. Okay, now this is the important point. LBAs can recognize only those languages which only need that amount of bounded space. If in case the language requires more space to check whether the strings are elements of that language, then you will not be able to represent it using linear bounded automata. Okay. Now we are going to look at the properties of linear bounded automata, decidability, closure property, and deterministic versus non-deterministic LBA. Decidability, okay, it is total. In the case of LBAs, decidability is total. All LBAs halt on all inputs because the tape is bounded. There is no infinite loop possibility. So somewhere there should be either an accept or a reject. It should stop. They're not saying that all inputs should be accepted. They are saying that all inputs must have a halt. Okay, so there is no because we have a restriction in the tape size, there is no possibility of infinite loops. Okay, that is decidability. It is totally decidable. Closure property. These properties, we are not going to go into details. Just to see the property, closure property, the LBAs are closed under union, intersection, and complement, and not closed under homomorphism. That means replacing one string with some other string. That is not possible because this is context sensitive. There it is not closed. Okay, then deterministic and non-deterministic, only one thing. Non-deterministic LBAs are more general and more powerful than deterministic LBAs, and it is a debate whether all non-deterministic LBAs have got an equivalent deterministic LBA. That is called the open problem or the LBA problem. Okay, and this is still open question in complexity theory. So we cannot say that there is an equivalent deterministic linear bound automata for every non-deterministic linear bound automata. Okay, and with this, we are concluding today's lesson.